tightness of the weight distribution bounds for polar and affine polar graphs.
That good? Can everybody see that? Sorry, just quick check. Okay.
Oh yeah, sure, please, yeah. So everything is fine, right? Yeah.
Okay, cool.
Okay,
Okay,
good.
yeah. Okay, yeah. Thank you for inviting me to speak today. And yeah, so hello, I'm Rhys, and I'll be talking about tightness of the weight distribution band in polar and affine polar graphs. So this is joint work with Sergei Goryanov and Leonid Shalanginov. And it's still in the early stages. So my talk will mostly consist of background on the weight distribution band and introducing in some detail the classes of polar and affine polar graphs. And along the way, I'll show you some results we found on the tightness of weight distribution band in these classes of graphs. So let me start with the weight distribution band, and first we'll look at distance regular graphs quickly. So just some notation to start with. Given any graph with vertices V and E, and two vertices in the graph, then D of U, W is the distance between U and W, and gamma I of U will be the vertices that are of distance I from U. And I'm sure many know, have already seen this before, but a connected graph gamma with diameter D is distance regular, and we have intersection numbers Ci, Ai, and Bi for all integers from 0 to D. If we can take two vertices, any two vertices in the graph, and if their distance, the distance between them is I, then we have that these intersections have cardinality equal to the intersection numbers of the graph. So one more thing we need to know before introducing the weight distribution band is some notation on eigenfunctions. So given a graph gamma and a function on the vertices into the reals, will be the adjacency matrix of gamma is denoted A of gamma, and the eigenvalues that we're interested in will be the adjacency eigenvalues. So the adjacency matrix is of interest. And then we also have defined the supports, or a sup of F, to be the values, sorry, the vertices such that F is non-zero on the vertex. And then an eigenfunction. So given an eigenvalue theta of the graph gamma, the function on its vertices into the reals is a theta eigenfunction if it's not identically zero, and for all vertices this equality is satisfied. So it's fairly easy to see that such a function is equivalent to an eigenvector of the adjacency matrix of the graph. And now we can define the weight distribution band and see why it's useful. So Kotov and co-authors introduced this band in relation to a study of certain substructures in graphs called bitrates. And in particular, he uses, so he defines the weight distribution band as follows. So given a distance regular graph gamma with diameter D and intersection numbers Ci, Ai, Bi, and eigenvalue theta, then the weight distribution band of gamma associated to theta, I will denote as WdV of gamma theta and is given by this sum where the wi are defined recursively with respect to the eigenvalue and the intersection number of the graph. And we're not that interested in the form of the weight distribution bound in this talk, but why it was interesting is because Krotov et al. Proved that any theta eigenfunction of the graph gamma must have cardinality of support at least the weight distribution bound. So eigenfunctions in general have been studied in relation to many substructures and in many classes of graphs. Many references can be found in this survey of Sotnikova and Valijanich if you need for any motivation. But in their survey, they focus on the minimum support problem, or the MS problem, which you can ask for any given graph. And so the MS problem asks for any graph gamma with eigenvalue theta, what is the minimum cardinality of support of a theta eigenfunction? And so this pops up, for example, in Krotov's work on bitrates, such eigenfunctions, sorry. And in many cases, it's interesting to characterize eigenfunctions with minimum cardinality of support. So what's known so far? Well, here's the list, I believe is quite a comprehensive list of the known solved cases of the MS problem. I won't go through all of them myself, but for example, for most Hamming graphs and all eigenvalues, the MS problem has been solved. Or the Johnson graphs, say, with the least eigenvalue, or all eigenvalues at least asymptotically, the MS problem is solved. And several classes of strongly regular graphs, for example, the Paley graphs and some generalized Paley graphs, and the least eigenvalue. And in this list, the cases 1 to 6, in these cases, all eigenvalues with cardinality of support, minimum cardinality of support, are characterized. So obviously, if we have a eigenfunction with cardinality of support equal to the weight distribution bound, then we've solved the MS problem. And the cases in the previous slide for which the weight distribution bound is tight are given in this list. So again, for example, the Hamming graphs and the least eigenvalue, or the Paley graphs and their eigenvalues, and so on. And in this list, the least eigenvalue of graphs often pops up. And part of the reason of this being we know the structure, or more of the structure, of a given eigenfunction with cardinality of support equal to the weight distribution bounds, which I will show you here. So first, some notation. So for disjoint subsets S and T of a given set V are called the difference indicator function, and denote it by F sub S union T. It's a real value function on V, and F S and T will be equal to 1 if V is in S, minus 1 if V is in T, and 0 otherwise. And I call it, this is just the difference indicator. It's called the difference indicator function, for me anyway, because it's the difference of indicator functions. And why is this useful? Well, Krotov, again, in his work, proves that given a distance regular graph with the least eigenvalue theta, then f is a theta eigenfunction with cardinality of support equal to the weight distribution bound. Then up to a scalar, f is the difference indicator function for some disjoint independent sets S and T, such that the union of S and T induces a distance regular graph in the original graph gamma. And this will be useful in a moment when we talk about strongly regular graphs, and in particular primitive strongly regular graphs. So just let me introduce what these are. So first, given a graph gamma, the complement will be denoted as gamma bar, and then obviously with gamma bar has vertices, vertices of gamma, and edges, exactly the non-edges of gamma. And then a primitive strongly regular graph will be, in this talk anyway, will be defined as a distance regular graph with diameter 2, such that the complement of the graph is connected. And the eigenvalues of strongly regular graphs are very nice. So a primitive strongly regular graph has 3 distinct eigenvalues, say k, rho, and sigma, with k greater than rho, which is greater than 0 and greater than sigma. And these 2 eigenvalues, rho and sigma, are called the non-principal eigenvalues of the graph. And strongly regular graphs also have nice complementary properties. In particular, as given a strongly regular graph, the complement of the graph is also strongly regular. So now, if we just, I'll just give a quick remark that if we take any primitive strongly regular graph with eigenvalues k, rho, and sigma, and the complement of that graph with eigenvalues k bar, rho bar, and sigma bar, then taking the weight distribution bounds, we see that both gamma and gamma bar have the same weight distribution bounds up to some permutation, depending on how you define the eigenvalues. And so using this with the results on the least eigenvalue of distance regular graphs and the weight distribution bound, we get the following useful result. So given a primitive strongly regular graph gamma with eigenvalues k, rho, and sigma, then if f is a rho eigenfunction satisfying this such that the cardinality of support equals to the weight distribution band, then we must have isolated cliques S and T, each of size rho plus 1, such that the f is the difference indicator function of S and T up to scalar, so time to scalar. And if f is a sigma eigenfunction with cardinality of support equal to the weight distribution bound, then there is a complete bipartite subgraph of gamma with parts S and T, each of size minus sigma, such that f is the difference indicator function of S and T up to some scalar. So isolated cliques just means that the two cliques have no edge between them. And so in the rest of the talk, I'll be mostly using the first, well, I will always be thinking about the first case in this lemma and using this to give our main results. So we're usually looking for isolated cliques in our given graph. And the first class of graphs we'll be interested in are polar graphs. So I'll be introducing their definition. And so for that, we need to know what a polar space is. And for that, I will also introduce at least the language I'll be using to talk about projective spaces. So given an integer d, at least 1, and a prime power q, fq will be the finite field, obviously, and pg d minus 1q will denote the projective space of which has dimension d minus 1, and it's defined over the vector space fq to the d. So in particular, the points of PG are the one-dimensional subspaces of the vector space fq to the d, and the L minus one-dimensional subspaces of PG are the points of or correspond to the L dimensional subspaces of fq to the d, and lines are one-dimensional subspaces of PG, so correspond to two-dimensional spaces of the vector space. Okay, great. And now I will introduce the definition of polar spaces. In particular, I will give the definition of a Vacant-Tits polar space. So a Vacant-Tits polar space of rank n greater than 0. So it is a pair P and sigma where P are the points of sigma and sigma are the singular subspace, points of pi, and sigma is the singular subspaces of pi. And a singular subspace is just a subset of the points. Such that we have 4 axioms. So the first, for any singular subspace, L together with the singular subspace contained in it, this defines a projective space with dimension at most n-1. The second axiom says we're just closed under taking intersections in sigma. The third axiom is quite important for us. So for all, it says that for any singular subspace with dimension maximum of maximum dimension, so n-1, and any point A which does not lie in this singular subspace, we have a unique singular subspace which contains the point, and the intersection of our singular subspaces L and M are nearly maximal, so of dimension n-2. And in this case, we know what the intersection of L and M are. And finally, the fourth axiom is just a non-degeneracy axiom. It says that there exists 2 singular subspaces such that they have trivial intersection and maximum dimension n-1. So in the literature, there's another definition of polar space called the Buchenhaut-Schult polar space. But there's a classical result that shows that these 2 polar spaces are equivalent. And in my talk, I'll use the next definition, although I don't know how widely used it is. So a polar space pi with points P and singular subspaces sigma will be called classical if there's an integer d at least 1 and prime power q such that the points lie in the Zargesian projective space, so PG a d-1 q, and the points span this projective space. So this condition is also called, for pi, it's the same as being embedded in the space PG, and it's equivalent to being a finite embedded polar space of rank n. So now let me give some nice properties of polar spaces. But first, so given a polar space pi, distinct points A and B pi will be called collinear if, of course, there's a singular subspace with dimension 1 that contains them both. And then we have the following properties of a classical polar space. So for our classical polar space of rank n, any maximal singular subspace has dimension n-1. Any set of pairwise collinear points can be extended to a maximal singular subspace. And there exists a parameter t, at least 1, such that for all singular subspaces R with dimension n-2, there are exactly t plus 1 maximal singular spaces that contain Al. So we will also give these useful definitions on some parameters we'll be using for counting things in polar spaces. So for a classical polar space pi, the order of pi is the pair q and t, where pi is embedded in PG d-1q, and t is the number of maximal singular subspaces containing a fixed singular subspace of dimension n-1. And then this parameter e pi will be just used briefly later on in our counting arguments. So all classical polar spaces of rank n is greater than 2 have been classified up to isomorphism, and here is a table of the standard representatives of each class of polar space and their related parameters. So for example, since an eclectic polar space is defined over a vector space order 2n and has order q. Later on, we'll see the hyperbolic orthogonal and the elliptic orthogonal polar spaces when we're talking about affine polar graphs, but at the moment we won't see any of the definitions of these spaces. And finally, we define a polar graph. So given a polar space pi with points p, the polar graph of pi will denote by gamma of pi, and it has vertex sets points p, and distinct vertices are adjacent if and only if they are collinear in pi. And in the case of a classical polar space of rank n and order qt, the polar graph on pi is a primitive strongly regular graph and has non-principal eigenvalues rho and sigma given here. And in particular, rho is always larger than sigma. So now we can study the weight distribution bound in these polar graphs. And in particular, we study the tightness of the weight distribution bound for the second largest eigenvalue. So given a classical polar space of rank n and order qt, and the polar graph pi, gamma of pi, then we have second largest eigenvalue rho, which is q to the n minus 1. And by our lemma in the first section, any rho eigenfunction of the graph with cardinality of support equal to the weight distribution bound must correspond to isolated cliques, two isolated cliques of size q to the n minus 1. And so first, we try to find the isolated cliques of size rho plus 1, and these are actually quite easy to find in our polar graphs and characterize with respect to the singular subspaces of the polar space. So in particular, given our polar space and polar graph gamma, cliques S and T of gamma, each of size q to the n minus 1, are isolated if and only if there are distinct singular subspaces such that their dimension of the intersection is n minus 2, and the union of the cliques is the symmetric difference of the two singular subspaces. This follows easily from the properties and axioms of the polar spaces, and the proof goes roughly as follows. So first we note that any singular subspace is a collection of collinear points, and so maximal cliques of the graph gamma are maximal subspaces of the polar space pi. We also see that a clique of size q to the n minus 1 can't be contained in a maximal subspace, a clique of size of dimension n minus 2. So it must be contained in a unique maximal clique. And two maximal cliques of these sizes are isolated if and only if their intersection has dimension n minus 2. So this was nice and easy. So we found all isolated cliques in this graph with respect to the singular subspaces of the polar space, but we don't know if the difference indicator function gives a row eigenfunction, but this is in fact always true. So, or we state that any distinct singular subspaces, M and N, such that their intersection has dimension n minus 2, the difference indicator function is always a row eigenfunction of the graph. And this follows immediately from the axioms of the polar space. And so with these two lemons together, we have the following. So first, take our polar space pi with rank n order qt and parameter e to be this e pi, and then take our gamma to be the polar graph on pi with second largest eigenvalue rho. Then we have that any row eigenfunction with cardinality of supports equal to the weight distribution bound must be from the difference indicator function of the symmetric difference of two unique pair of maximal subspaces with the dimension of their intersection equal to n minus 2. And because of the nice counting properties of polar spaces and polar graphs, we can actually count such isolated cliques and show that there are exactly this many row eigenfunctions with cardinality of support equal to the weight distribution bound up to a scalar, of course. Okay, so we've finished working on the polar graphs, and now we'll move to affine polar graphs. And so I will try to use some information I've given about the polar spaces to help us understand the structure of affine polar graphs. So first, we'll introduce some information about quadratic forms. So the setup is we have a vector space, the vector space f q to the 2m for some integer m at least 1, with the non-degenerate quadratic form q of type plus or minus 1, so this is hyperbolic or elliptic, and then this function b a q defined by this equality is symmetric and bilinear, and by definition of Q being quadratic. And we also have that BQ of UW G equals to 0, which is also equal to Q of U for all W in the vector space if and only if U equals to 0. And that's the definition of non-degeneracy of the quadratic form Q. And now it'll be useful to know what the quadric is in this vector space. So we call the quadric Q of V is the set of vertices of V such that Q is equal to 0 on the vertex. And it's useful to note that 0 is obviously in the quadric. So we have this vector space and we have the quadratic form. We can now define the orthogonal polar spaces. So the polar space O with parameters epsilon, 2m, and q has singular subspaces. We will denote by sigma of epsilon, consisting of the subspaces of PG, so 2m minus 1 and q, such that q is identically 0 on the subspace, basically. And points of our polar space will just be the 0-dimensional singular subspace of the space. And in particular, the R-1 dimensional singular subspaces of the polar space O epsilon are the points of an R-dimensional subspace which lies in the quadric of V. And now we also define what an affine polar graph is. So given our vector space V and quadratic form Q, the affine polar graph, VO epsilon with parameters epsilon, 2m, and q, is the graph with vertex set the vector space V and distinct vertices U and W are adjacent if and only if Q of U minus W is equal to 0. And this is another standard construction of a strongly regular graph. So the affine polar graph is a primitive strongly regular graph, and it has non-principal eigenvalues theta 1 and theta 2 here. And this time, theta 1 and theta 2 do not have theta 1 is larger than theta 2 if and only if epsilon is equal to +1. So we'll have to take cases on epsilon later on. So how does knowledge of the polar space help with understanding the structure of our affine polar graphs? Well, if we have two independent, so we can actually see the singular subspaces of the polar space as a subsets of vectors of the quadratic. In particular, given independent vectors U and W of the quadric, then they define two collinear points in the polar space if and only if, well, by definition, they span a subspace which is contained in the quadric, but this is equivalent to Q of U minus W equals to 0, which is, of course, the definition of being adjacent in the affine polar graph. So from this, we can identify singular subspaces or any set of pairwise collinear points of polar space O of epsilon with a clique in the affine polar graph VO epsilon. And what about the other way? So we know what the singular subspaces look like in our affine polar graph, but what can we say about the rest of the graph? Well, first we remark that for any three vectors or vertices, v, u, and w, then u and w are adjacent, of course, if and only if u minus v and w minus v are adjacent in our graph. This is obvious because u minus w is equal to u minus v minus w minus v. And so from this, we can see that any clique C in our graph and vertex in the clique, the vertices of C minus V form a clique in our graph. And because now 0 is in C minus V, we must have this clique C minus V as a subset of the quadric. So we can, from there, we can actually extend it to some singular subspace. And so in the rest of my talk, what we will do is go from projective to affine world by identifying a singular subspace of our polar space O epsilon with the underlying vector space, which is contained in the quadric, and refer to the vector space dimension of spaces instead of the projective dimension we have been talking about previously. And now, like I said, we'll have to take cases on epsilon. So first, we study the weight distribution bound in the affine polar graphs VO plus. And again, in particular, we will study the tightness of the weight distribution bound for the second largest eigenvalue. So in this case, our graph has second largest eigenvalue rho given here. And we are looking for isolated cliques S and T of size rho plus 1 is equal to this q to the m minus q to the m minus 1. But actually, we're in a very similar situation to that of the polar graphs. So first, let's take our affine polar graph gamma to be VO plus and second largest eigenvalue rho. And then remember, we can take the singular subspaces sigma plus embedded in the vertices of gamma. And then we find that cliques S and T of size rho plus 1, so q to the m minus q to the m minus 1, are isolated if and only if we have a vertex V and distinct singular subspaces such that the dimension of their intersection is 1 less than maximum possible, so m minus 1, and their union is an affine shift of the symmetric difference of the two singular subspaces. And again, we find that for any vertex V and distinct singular subspaces M and N with dimension just submaximal, so of dimension m minus 1, then the difference indicator function of V plus the symmetric difference of M and N is always a rho eigenfunction of gamma. So this is basically saying that all of the isolated cliques that we're looking for are just translations of the isolated cliques from the polar graph. And so we have the following results. So any rho eigenfunction of our graph with cardinality of support equal to the weight distribution bound is the difference indicator function of V plus the symmetric difference of M and N for some V and unique pair of maximal singular subspaces M and N with dimension of intersection equal to M minus 1. And again, we can count all such isolated cliques and show that there are exactly this many row eigenfunctions of our graph with cardinality of support equal to the weight distribution bound up to a scalar. And finally, we'll ask the question of what the weight study the weight distribution bound in the affine polar graphs VO minus. And so in this case, our graphs have second largest eigenvalue rho equal to q to the n minus 1, and we are looking for the isolated cliques, two isolated cliques of size q to the n minus 1. But this is different to the case where epsilon equals to +1, because such cliques of this size are actually maximal cliques. And so we can't get the same construction here as we did previously, and we'll need one more definition about these vector spaces. So basically the definition of orthogonality. So first take the singular subspaces sigma epsilon in our polar space O epsilon embedded in our graph or the vector space. So first we define perp. So for a subset of the vector space U, U perp is obviously the vectors in the vector space such that for any U in vector in U, BQ of U and V equals to 0. So they're orthogonal. And it's useful to note that in this case, if we take a maximal singular subspace of our polar space, then M is always a subset of M perp, and M perp is a subspace of the vector space and has dimension, so equal to the dimension of M if epsilon is equal to +1, and the dimension has dimension the dimension of M plus 2 if epsilon equals to -1. And this might suggest why we weren't interested in this when considering epsilon equals to +1. But in this case, it's needed to characterize the isolated cliques of our size. So in particular, any two cliques S and T of our affine polar graph of size q to the n minus 1 are now isolated if and only if we have two vectors, u and w, and one singular singular subspace M, such that S is u plus m, T is w plus m, and the difference u of u and w lies in M perp, but not M. But this characterizes all isolated cliques of our given size again, and we have again that for any u and w and any singular subspace M with their difference in M perp, not M, then the difference indicator function coming from this construction is a row eigenfunction of our graph, sorry. And so we have the last of our results. So any row eigenfunction of our affine polar graph VO minus with cardinality of support equal to the weight distribution bound has to be equal to the difference indicator function of u plus m and w plus m up to a scalar, of course, for unique maximal subspaces M, for a unique maximal subspace M, and two vectors u and w such that their difference is M perp, but not M. And we can count such isolated cliques, show that there are exactly this many row eigenfunctions of VO minus with cardinality of support equal to the weight distribution bound up to a scalar. So we're at the end. So let me just recap what we do in these graphs. So for any polar or affine polar graph with second largest eigenvalue rho, we first noted that eigenfunctions with cardinality of support equal to the weight distribution bound come from certain isolated cliques of size rho plus 1. For each of these graphs, we characterize such pairs of isolated cliques with respect to singular subspaces of an underlying polar space. We then show that any of these pairs of isolated cliques define a rho eigenfunction, and so we get a rho eigenfunction with cardinality of support equal to the weight distribution bound, and we can count all such pairs of isolated cliques, and so count the sort of different rho eigenfunctions with minimum support. And so what further work do we have? Well, we haven't talked at all about the least eigenvalue of these graphs. So all is unknown still, I guess, although we will hear something, I believe, later on in Sergei's talk about this case in certain affine polar graphs. But we still have to answer these questions in general. So first we ask, are there any sigma eigenfunctions, where sigma is the least eigenvalue of the graphs, with cardinality of support equal to the weight distribution bound? Of course, if we answer this in the positive, then we answer the second question. But otherwise, we ask, what is the minimum support of a sigma eigenfunction? And once we found eigenfunctions like these, with this property, we might want to ask if we can characterize sigma eigenfunctions with minimum support. And more generally, we could be looking at different classes of strongly regular graphs or strongly regular graphs in general. So it might be interesting to study eigenfunctions of, say, graphs or other graphs related to polar spaces, or we might want to extend the known results on eigenfunctions in the case where we restrict ourselves to strongly regular graphs, or maybe even generalize some results we have with strongly regular graphs to other families of graphs. Okay, thank you. That's the end of my talk.
Oh, such a wonderful talk. Thank you very much. Thank you, Rhys. Are there any questions to Rhys? Well, I just wondering, well, of course it is a stupid question in some way, because, well, you see, do you think that your results on clicks in some way it could help in getting some progress on the problem which was stated in the first talk?
Probably not.
No.
So, yeah, I believe if they are connected, it would be that they, sorry, Chi, I think, Chi will be working with sort of a more general class of graphs, so much more general. And so these polar graphs are very nice because, for example, any clique will be contained in a canonical maximal clique, and all these maximal cliques just come from maximal subspace. So these graphs are really nice. And the reason why these rho eigenfunctions are so maybe easier than the sigma eigenfunctions to study is because we're talking about cliques and subspaces, and therefore subspaces of the polar space. So they're much easier to handle in these graphs than many others. So yeah.
Right, yeah, right, okay. Any other questions? If not, then let us thank again Rhys for this wonderful talk, and thank you very much for teaching us on polar graphs and polar space. Thank you very much. Yes.
Thank you.
Yeah.